Bam! And we're live. Welcome back to StarTree. My name is Victor Gamov, and I'm head of developer advocacy here at StarTree. And I'm happy to host this fantastic meetup where my friendly colleague Hubert Dilly gonna be presenting some cool stuff. Hubert, welcome to live stream.
Uh, Thank you for having me. We're super excited to really talk about Gen AI in real time, and yeah, excited.
That's cool. Before we jump into presentation, so I would like to get a few seconds for people to settle and just like introduce themselves, where they're coming from, what's geography of our talk. Usually, we're trying to accommodate different time zones so the people can join the different places during the time that's very convenient for um, their work schedule or work life schedule. So, folks, we are supposed to be streaming on multiple locations. If you're coming from LinkedIn, let us know you're going from LinkedIn. Oh, yeah, okay. Max is here.
Hey, Max.
Max is, as you can see here, he coming from the
Hey, Ben.
LinkedIn. Jordan is also in the house. Great. Max is in Germany. Fantastic. At least 9 people alive. Like me and Hubert coming to you live today from the East Coast of United States. The Barca join us today also from East Coast, a little bit on the down the south from the Florida. Welcome, Barca. Yarden is coming to us live from Lisbon. This is incredible. I've been there just almost a week ago. We did a meetup there. It's a fantastic town, fantastic place. Um, so, folks, we have a very packed agenda. Don't hesitate to ask your questions along the way. We will not highlight everyone, but I will be here in the background watching and listening everything, and maybe even trying to interject some of the questions if there will be questions that will be super pressing and we need to address them immediately. But as Hubert mentioned this before this presentation, he has a lot of things to cover, so we're going to start with a presentation. And I see a bunch of people joining. Wow, this Singapore, fantastic! I'm planning to go there at the end of the June. Hopefully, we'll see you in person. It is Sukalpo. I hope I'm not butchering your last name. We do have someone from San Francisco. Welcome. And someone from North America. That's pretty vague. Anyway, so with further ado, I'm passing microphone to Hubert.
Awesome.
And Hubert, can you run the slides from here from this UI?
I don't
Let's
know.
try if you're able to do this. Otherwise, as a backup, we will just switch to the screen sharing and we'll go from that. How about that? Can you click
Yeah,
around
I
here?
don't. Yeah, I don't see controls.
It should be
Where?
it should be on top.
Well, I moved my arrows, so it looked like it advanced.
Okay,
Yeah.
perfect. Yes.
Okay.
So it works. I'm here around. I'm chatting with people in the chat, but stage is yours.
Perfect. Um, Towards the end, I will need to share my console just so that people can see um, how and what is going on. But we'll tackle that. We'll tackle that later. Um, this slide here is just to remind myself to start up the recipe. You'll be able to find this recipe in the Star Trees GitHub account under Pinot recipes / Gen AI. We'll have the link there later. Just to create a good foundation for all of us to ask questions and understand, I'm just going to go over these basics on vector databases so that um, later slides will make more sense, okay? So what is a vector? A vector basically is an array of numbers, most likely float numbers. So that's just basically a vector. It's a math component that allows you to work with data. What is an embedding? Well, an embedding is a vector, but embeddings are typically created by models that take unstructured data and creates vectors out of them, which we call embeddings. These models take unstructured data like text or videos or images. They try to make sense out of it and then build you this numerical representation of what the representation that describes that unstructured data. Unstructured data is typically something that you can't ask questions of. Like I can, for instance, a JSON message has fields, and I can ask, the first name of a, first column or second column or so on. You can't really do that with unstructured data. There's no structure to it, so you need something to give you some kind of like understanding, and that's what an embedding is. What's a vector index? Um, Basically, it is a way to make lookups for vectors in a database really quickly. And a vector database is basically encapsulates all of these features into a single database. Let me just go into these things a little bit more. Waiting for change. So what is a vector? Here's an example of a vector down here. It is unstructured. So the first S1 there is I love data, and the second one is I love candy. You can actually break that down into two columns, like the ID of S1, S2 as sentences, and then candy, data, I love. You can see that I just marked one, like the number of instances of these terms in that sentence. And already you can see that it has a similarity of I and love, if they both have those terms in there. So this is an example of what you could see as a vector that represents unstructured data. But embeddings actually go a lot further. They are like neural networks or some kind of model, a machine learning model that represents data. Unlike what a bag of words, which is what I just showed you, represents. For instance, if you say something is good or not good, you could get some bad results if you use a bag of words, because good and not good will be similar to one another, even though semantically they are complete opposites. So this is why you would want something like an embedding to make sense out of the content or the unstructured data that you're wanting to learn about. Again, index, we all kind of know what an index is. It's a way to be able to retrieve data out of a database in particular, to get them really quickly. Well, vector index is exactly that, but for vectors in a database. And again, a vector database just encapsulates all of those ideas into a single application or service. So the difference between when you add similarity search to a database is that you're mixing exact match versus similarity search, or similarity matches, right? For the first line there, select foo from bar equals baz. That's an exact match. You're not going to get rows where bar doesn't equal baz, right? Similarity search actually is a bit different. You actually need another input to be able to get these results back, and that's value. That input is distance. How close do you want your results to be to the actual exact match? So for instance, if it's zero distance, that means it is an exact match. If it's like 100, that means you're 100 uh, units, I guess, away from exact match. You have to decide how far you're accepting results for the database to return. And I'll get more into detail of what that means. But here are some of these distant algorithms that Apache Pinot is implementing. There's L2 Euclidean distance. So in the top box up there, you'll see both Euclidean and Manhattan. Basically, it's a triangulation to get distance between A and B. If A and B were the same, obviously the distance would be zero, and it's an exact match. This is you're trying to get the distance. How similar or how different are A and B together? A Euclidean distance is a straight line, right? But a Manhattan distance is there's obstacles in the way. Basically, imagine if you were in Manhattan and you were trying to get from A to B, you wanted to know the distance. A Manhattan distance is going to give you probably a bit more accurate distance calculation versus a straight line, because the straight lines don't exist in Manhattan, right? That's how it got its name. Cosine is in that space. You see in the bottom right hand corner there is the angle, the measurement of the angle between those 2 points. So the further they are, or the closer they are, the angle will be would correlate to how far those 2 points are. Dot product is a bit more. It's kind of similar to Euclidean, but it's just I guess a bit less complicated distance algorithm. We use these algorithms to kind of figure out how far things are, so that when you query a database, they return those thresholds only to you. So we're in the context of real-time RAG. Well, what is RAG? So RAG stands for Retrieval-Augmented Generation. It's a popular term being used today in generative AI. Basically, what it means is that we need sometimes LLMs need additional help to be able to provide more information on the questions that is being given, right? And sometimes we want to know the sources that the answers or the responses that LLMs provide. Where did they get this information, and how can we, ensure that they are actually correct? Well, in order to do that, you need a RAG. You need to help facilitate that capability with LLMs. Another point is that these LLMs, they actually take months to train. So by the time they're done, uh, you're not going to have a lot of the information that occurred in the past 3 or 4 months it took to train that. And having the compute and the storage to build these or to train these LLMs, you could imagine they're in the tens of millions of dollars. So they're not going to have yesterday's information. They're not ever fresh. So how can we make RAG or the responses from an LLM be real time? Well, that's real time RAG. We'll get into that more in a second. So LLMs with RAG, we could supplement more information to the LLM so that their responses are more accurate and more fresh when it responds with these answers. Okay. Great. And we're also going to kind of look at LangChain, which is just it's a framework to build applications. You could pull in models from different sources, like the llama there is for Olama, OpenAI, and Gen AI we're all kind of familiar with, Hugging Face and I can't pronounce that name. I can't remember exactly what that name is. But these are common LLM providers that you can call and use out there today. And LangChain kind of helps you use those. They also help you use vector databases. It's just a way to bring everything together into a single application. And in this case here are some of the vector databases in the market. You can see kind of where everything falls. But if you notice, Pinot is up there with like Cassandra and OpenSearch and Postgres. This is not animated, but you get the idea. There's it's open source, Apache licensed, and has full database support. Okay, great. So now it's time for a demo. How do I get to console? Victor, I think you're muted.
Yes, you're right. That's very amateur. So you want to share the screen, and we will switch to.
Sure. So we'll need to share both some browser tabs and a console. Great.
Sweet. We have a inception mode now.
So this is where you can find some of the recipes in Star Trees. Just go to Star Tree data in GitHub and go to Pinot recipes. And under the recipes directory, you'll see Gen AI directory that kind of goes over how this works. What we're going to do is do a real-time RAG demonstration where we consume contents of a website. And we use tools like LangChain. In this case, we're using OpenAI as a way to, as the LLM to use. We're going to use Kafka as well because we're mimicking a real-time use case where we're consuming data in real time and sending it to Apache Pinot, and then we do our search against Apache Pinot in combination with OpenAI. I've already done this, but I stood up my recipe. So you just make recipe, and then you can load different websites to your to Apache Pinot. What this will do is create embeddings out of the content of the URLs of
Can you
each
make
web
a
page.
can you make a font bigger a little bit?
Oh, sure.
So yeah. And also,
So
we don't
here,
need probably the sidebar with files. You can close it and make the font bigger so people will see it.
there you go.
Perfect, fantastic.
Great. So all you would need to do is just stand up the infrastructure and then start loading data as you want them. There is some caveats here, and I'll get to them a little bit later. But this is what we're going to do. Is I'm going to switch to the command line right now. Here. So can you guys see the recipe or that my console here?
Highly recommend to make font bigger as well.
Oh, let me do that here. Okay, I hope that's visible. So what this does is just stands up Kafka, stands up Apache Pinot, and then starts just preparing the infrastructure so that you can start using data or start asking questions. So the way you ask questions is you can make questions or as a question, and it'll start loading the application, and then you can ask questions against Apache Pinot and OpenAI. So what is Apache Pinot? Notice I haven't really loaded anything in the database yet, so it's going to tell you that it can't find anything. There's nothing here to understand. So let's do this. Let's load a web page. In this case, we're going to load this page here. The indexes you can find in Apache Pinot. Okay. So what this will do is it will use inside LangChain this thing called the recursive URL loader. It takes a URL, it recursively loads pages that's within that domain, in that domain context, and then send that to my application, and this application is going to convert them into embeddings, send it to Kafka, and eventually into Pinot. We're mimicking a real-time pipeline here that listens for like changes in the website and sends that information to Kafka and ultimately into Pinot. Right. So it looks like it finished. So let's ask this question again. What is Apache Pinot? So open source data analytics platform. So I only gave it some basic information like on indexing. So let me give it more context. And I think in the website or in the application or on the slide here, actually, I have some things I can copy and load. Let's load another in here. So as we're loading, we can ask this question again. What is Apache Pinot? And it'll give you a bit more accurate response. Okay. What are some indexes in Apache Pinot? So we could see there's a Bloom filter, forward index, geospatial index, inverted JSON. So it looks like it's working, and we're getting this information in real time, right? Let's say if we wanted to change some of our documentation, let's say your chat GPT that you're creating for your own app, for your own business has changed, say, hours or has changed in some of this documentation, or in our case, and a couple of weeks ago we had our TA summit. Let's say sometimes our rooms were changed. How can I get that information immediately, right? So this is how you do that. You load that data, you listen for changes, load it into Pinot, and then Pinot will overwrite because it's using upserts, it'll overwrite some of the records that you have in there already, so that it's returning only latest records, right? Let's look at the what's happening in the code. So this is what the loader looks like. Takes data out, it recursively loads a URL, and then starts writing into creating embeddings and writing it into Kafka. And that's what this looks like right here. So I have a recursive loader. Oops. Recursive loader. You're going to have to wait for this this recursive loader to finish. So if you have a big website, it might take a little bit for it to finish. You may want to implement your own recursive URL loader. This one's just convenient to it's just available to use. Otherwise, there are some extractors for pulling out text that you can use. And at the end, you have documents that that this recursive loader has loaded. In those docs, I loop through each one and create a message to send to Kafka and ultimately into Pinot. I know where the URL that I found where this document lives, the content of that web page, and some metadata that goes along with that page. Here, I'm creating an embedding out of the page content. If you go up here, we have this client creating embeddings, and I'm pulling the embeddings out of it. What this client is OpenAI over here. So I'm using OpenAI. So you're going to need some tokens, right, in order to invoke this, because it will call out to OpenAI and get and to create embeddings out of your data. Right? Alternatively, you could use something like Olama, which is a locally hosted LLM that runs locally next to your application. So in that case, you wouldn't need a token or have to pay for that service. But basically, this is how you create an embedding. Okay? And then we write that embedding into, in this case, a Kafka. All right, so that's the loading side of the pipeline. So this is the application. This is the Gen AI application. So there's a few things here to kind of understand. So first, we are asking a question. Okay, and we have a link to our we have a connection to Pinot as a Pinot vector, and this is the question that we are asking, and we take that question and we do a similarity search on it. So let's look at what this is doing. So this is going into Pinot. We have a connection to Pinot right now, and we get a cursor. what we're doing is we're taking that question that we asked from the console, and we are also creating an embedding out of that. So we are now have a search embedding and an embedding in the database. Let's look at what's inside Pinot right now. You can see we have source, the content, some metadata, and an embedding itself. So let's look at, see, maybe I can make this a little bit bigger. Here's some of the content. We can look at the sources that we've loaded. We can look at the embedding, but that's not going to be too interesting. Again, remember, embedding is a vector, and the vector is just an array of numbers. So this is not something that you would want to type in an editor like this. It's not like a free form thing you would want to do. This number came from, again, a model that represents unstructured data. Okay. So when we go back to here, what we're doing is we're selecting from that documentations table, and we're doing a vector similarity. This is where we're leveraging Apache Pinot's vector index. And let's take a look at what that looks like when we created this this table. So here's our real-time table documentation. If you look down here, we have a configuration for our column called embedding. So we have an embedding field in our JSON that we sent. We have the index of type vector. And then we have the definition or the properties that go with that that vector. Okay, so this is the implementation. This is a type of vector that we're using. It's called HNSW, or hierarchical navigable small worlds. Not a term that you really need to know, but what you do need to know is that the other properties are more important. This is how wide the vectors are going to be generated. So you kind of need to know when you call OpenAI or whatever vector embedding model that you're using to create unstructured data into embeddings, you need to know how big they are, so that when you create your table, you apply that dimension in here. Okay. And again, when we talk about distance, we support 4 different types. In this case, we're using cosine distance for this particular vector index. So this is what makes vector, Apache Pinot basically return you very quickly vectors from this table using this vector index. To complete, we want to also show the schema, right? So this is the schema of the table. Notice that in this embedding column, it's not of type bit, it's just a float, and it's not a single value, so it is an array. So it's a float array. This is where we store the embeddings. Okay. And more importantly, just as important, is the content. Notice that the content is string, and the max length is 8,000. So you can set this to whatever number you prefer. I just know that when I generate embeddings, the embedding model can't consume more than a little bit over 8,000 characters max length, right? So this is something you need to know. If you don't set this, I believe the default max value is 512, and if you set it to that, you're only going to get part of the content when you send this information to your LLM. So make sure you're grabbing as much content as you can, so that when you send it to the LLM, it makes sense for it and responds accurately. Okay. Moving on. Now that we have understand that how the documentation table looks like and its schema and how we created it, what we're doing here is making it very fast to look up data in our vector table, in a vector column. What we respond with is the source and the content the metadata column, and then we perform a cosine distance between the embedding and the search embedding. Remember, the search embedding is our question, and the embedding itself is the content that we pulled from the website. We are checking to see how similar they are, right? That's what this index is doing, and this is actually returning the actual distance between the search embedding and the actual web page embedding, and that's going to get returned as a value for this cosine column. If you're not familiar with this notation, this with dist as, so this is called a CTE. In this case, we're creating a kind of a view or a table-like structure called DIST for distance, abbreviated for distance. It's a common table. CTE stands for common table expressions. So what we're doing here is we're selecting from DITST or dist, and we're only selecting where cosine is under the distance is under, in this case, 0.3. So these are basically what I'm saying here is are ways to tune your questions or queries against the against a vector database, in this case Apache Pinot, right? So a few things here really it helps you tune the distance and the limit. The distance actually also this should be a variable here. It should be I should have this is how many basically distance or layers to return to as a result. It may not return 10 or it may return a bit more than 10, but it's kind of a characteristic from HNSW, the way the algorithm works in returning results. And I'll get that into a later slide. But basically, you could tune this value here, this, the top K results, this distance value here, how close you want things to be as a result, and the limit. So the limit is important, and because the LLM has also limitations. If your content, if you give it more than 5, for instance, the content that you return from the content from this content here might exceed what the LLM can handle. Like if it returns, a lot of data or a lot of content, it might be too much for the LLM to understand or want to consume, and then it'll throw you, like a rate limit error saying this is too big. Reduce the content that you're sending me for me to answer your question, right? So you want maybe to limit it to maybe, in this case, I said 5. I may have like 20 results, but only order them by the shortest distance, asynchronously by cosine, and then give me only 5 of them to send over to the LLM, so that I'm not over my limit or the capacity of the LLM to respond with a response. Okay, I hope
Bert,
that makes
can you
sense. Yeah.
yeah, when you're talking about these like optimization and tuning things, can you show people how they can see execution time of the query using the query console? There was a question on YouTube, and I think it's a good idea to kind of demonstrate how they can see this on the query console.
Uh, s- uh, how to run this in the query console? You mean?
Not
And see
necessarily,
the
just you can show, so basically every time we execute query together with results set against some additional metadata. But if you go to query console and run the
Mhm.
query, you will see the execution time. Can you switch back to query console actually? And you have
Yeah.
some sort of query. Yeah, you see like the query response stats. This is where you get it's a you get different stats like how many segments were scanned and how much time it took, how many documents were scanned, and so forth, so on. So this is
That's
the
right.
question from Train Chen, and that's you will be able to see with any query. There's metadata there. It's easy to use, and you will be able to see. So you can tweak it to the way that you
Yeah.
want it. You can see how this will perform with enabled indexes, without enabled indexes, so far and so on.
Right.
So
Right. when you call this from a client, you're going to get these results. You're going to get some metadata, so like the schema and the rows themselves. And not only that, all the values that you see in the response stats, which is way down, um, which is really big because this is really all the way at the end. There you go. So you can actually consume these yourself. Total documents scanned, and et cetera, et cetera. So same thing up here. We just format it for you to view nicely.
Yep,
So
exactly. Thanks,
all
Hubert.
that's, yeah, sure. All that's available to you. So when this returns, when I execute this query, um, it's in this cursor actually contains all that information, right? I'm only asking for so here I'm building a data frame, and I'm using a data frame loader, and then so I'm basically taking the contents of the response back and then building a data frame out of the response from Apache Pinot. And I'm using that here and this results. If the results equal 0, then I print something I couldn't find anything. Otherwise, if I do have some data, this is where we start to talk about prompts. So what a prompt is, here's an example of a prompt. It's basically this. I'm saying answer the question based on the following context, and the context is the content that we pulled from Apache Pinot, or the similarity results. Basically, what we're doing is we're doing a similarity search in Pinot. We're getting the content we grabbed from the website and pasting it into here. That's why you want to be conscious of how much data you're sending over here, so that the LLM doesn't complain. And then we are so this prompt starts to gets to be really big. And at the end, we say, "Hey LLM, answer the question based on the above context," and then we paste the actual question that I typed out in the prompt at the end. All that information, you're kind of helping the LLM to understand, to respond appropriately, because you only wanted to respond based on the context here. And since this is basically real time, and you're constantly updating it using upsert features inside of that's basically how the table is created in real time. You're only ever going to get context in here that's fresh and up to date. Okay. So down in here, we're actually taking that content, and then we're joining all the page contents and putting basically a prompt template here. So this, and at the end, this is just a string. We're going to format that string and create a prompt. That prompt gets sent to OpenAI or the LLM here, and this is the response that you see, like the human readable response from the LLM. What we do here is we print the response here. And since we know the sources that generated the prompt, we cite all the sources ourselves. So this is not something what the LLM does. We have to actually provide the sources, because we know we own the connection to the Apache Pinot or the vector database. We know where everything came from. So we are saying this is the data that we use to send over as a prompt to the LLM. Okay. Any questions here so far? This is how we're building RAG, but we're incorporating a real time element to it. Let me go back to over here and
I
show
don't see
you.
any. I don't see any new questions in the chat, so I think we can assume that everything's clear. Yeah,
Okay,
folks. Every time when there's no questions, it's two things. If it's everything clear or nothing's clear, and without your communication, it's very difficult for me and Hubert to understand which one is which. So let's make some noise in the comments, and also let me check and see if the I don't see the stats on the LinkedIn, but hopefully people on LinkedIn continue to watch and ask their questions. So so far so good, Hubert.
great, thanks. So just going back to the schema, the way we define this table, we do have a primary key down here saying, hey, this is the primary key that to use. So every time you reload a URL, Pinot knows to change its pointer. Basically, you can't overwrite anything in Pinot, but it will update a new record and update the pointer and points to the latest record, so that when you select from it, it's returning you the contents of a web page that is most recent. Okay. In the table configuration in the bottom here, we have some upsert logic. We're saying that when you update a record in this table, we're saying that you could overwrite the embedding and you can overwrite the content. This will allow us to always have fresh data when we select from Pinot when we're generating the prompt for the LLM. Okay. I'm going to go back to here. So I'm going to present from here, Victor, if you don't mind. So this is what's happening. So we are loading a corpus of data, in this case, a website, and we're sending it through an embedding model, and then sending that to Apache Pinot, right? And Kafka is in here to allow this done over streaming. And when we ask a question, we are assembling a prompt. So the user asks a question, we convert that into embedding, and understand that we are using the same embedding model to transform this document to an embedding, and the question to an embedding. This is important to know because this ensures that these embeddings live in the same vector space, so to speak, right? You can't use a different embedding model to create embedding out of this question, and they can't be different, right? Because the vectors won't match. They have to be in the same vector space so that we could do similarity search between them for Pinot, right? If they're not the same, you could expect very bad results. So when we go into the similarity search, this is that query we invoked into Pinot. We have an embedding, and we're comparing the question embedding with the document or contents embedding, and then allowing Pinot to quickly, using its vector index, return the context over here to populate the prompt. And we take the user's question, we also append it to the prompt and send that to the LLM, and that's the response that you get from, in this case, OpenAI. Okay. We kind of went over this already. Here's the cosine distance. This allows you to tune the distance specifically. Basically, the smaller the distance, the closer it is, more similar it is. This is the vector similarity here is what makes the response really fast from Pinot. And a limit, again, limits the number of documents that you're sending over to the LLM. Top K, here number 10, top K is a parameter that we use to tune the HNSW algorithm. Basically what it is, it will return 10 of the most significant words, or in this case, vectors, in the vector representation of the document at each level of the hierarchy. So there are it's kind of hard to visualize this. So this is what a diagram kind of looks like. There are multiple hierarchies in this index, and HNSW index, and it kind of looks for each layer some vectors that are similar to the question, the embedding of the question. Okay, and that's it. You could actually do this on Startree Cloud free tier. So you can scan that and get a free trial, or a free forever actually. Shared instance of Apache Pinot in the cloud. I'm open for any questions.
So we do have questions from Sergey here. How generation of embeddings impacts throughput of Pinot?
The so sorry, say the question again. Oh, how generation of embeddings impacts throughput. So the generation of embeddings is outside the context of Pinot. So we are putting the embeddings into Pinot. The generation of these embeddings is outside of Pinot. So as far as throughput is concerned, we want to measure it from the query. So when we think of throughput, we want to measure query latency of Pinot. So the vector index is going to make that really fast. If you want generation of embeddings to be really quick, that's your stream processor or some other application that's calling or reading the applications or these web pages, generating the embeddings and then writing it into, in this case, Kafka to load into Pinot. So the generation of the embeddings isn't really part or doesn't really affect the throughput of Pinot at all.
Okay, so we're talking about David from YouTube is asking: is there any relevant differences between real-time and offline tables in schema or index?
So real-time tables basically allow you to do everything in real time. So think of Pinot as like a stream processor, like a Flink that's able to read data from a stream and consume it and have a state store and have you be able to quickly query it in real time. But it also has offline tables that's loaded from say S3 or some other data at rest um, um, system, right? So if you want to do this in real time, you probably want to do a real time table because you're updating records in real time. So you want that to always be fresh. Otherwise, you could do this same scenario loading segments from or loading Parquet files from S3 into Pinot. You'll get the same results, but it won't be as fresh because you're doing it via batch.
There's a few small differences, but it's a technicalities in the way how the ingestion works on Pinot. But there's no difference in terms of configuration or what kind of indexes you can use. There's some um, caveats of using star tree index on certain places, but in general, they are ultimately the same. So you will be able to query data from Kafka immediately. So, next question: artificial intelligence technology. Okay, someone is actually spamming here. All right. So the question is: can I use Pinot as a real-time online storing database for recommender system?
Yeah, absolutely. So Pinot covers both your Gen AI use cases as well as your analytical use cases, right? Like if you wanted to show the graphs of performance of everything, it's it's absolutely great for a recommender system, right? As long as you're imagine it this way: if you have an application that's serving like tens and thousands of users, um, you want something that's performant in the OLAP space as well as the vector database space, right? So Pinot actually can serve low latency queries um, for over like 10,000 end users. So if like it's used in LinkedIn to serve views and impressions. So you want that same kind of power capability from a recommender system that needs to query uh, uh, vectors or embeddings in a database so that it could return, for example, recommended products or articles or so on, right? Or even images. You could actually do the same use case, load a bunch of images, and then find similar images in your vector Apache Pinot.
One of the things that I like to say when the people asking about use case, so Pinot actually can be your last mile of delivering data to API. So, but you're not going to be exposing Pinot itself to users because it doesn't make any sense to expose, for example, Query Console or directly API. But the Pinot is a great choice of the database that will be powered API or front end of features that you will be delivering. So those things are work great, and the Pinot support all these capabilities of real-time analytical system where you have access to fresh data through the what the Hubert demonstrated through the ingestion through Kafka. Um, Data low latency. The Pinot queries are can operate with latency of hundreds of milliseconds or even lower, and with the massive concurrency, the access to those queries, the thousands and the hundred thousands of people can have, and Pinot will be able to respond with success. Right, we're going to next question. Is it possible, recommended, to add the generation of embeddings to field transformations? What do you think? I know my answer, but like I would love to hear Hubert opinion about this.
Um, what do you mean by field transformations? As in,
I
like
think
a
it's when they ask in kind of like if they can have a like a function that will do something with embeddings when you have this transform function when you define a schema,
hmm, I
you know?
see, like a materialized view where you have data and then you add a function to it, and then
It's kind of like, when you kind of say you have JSON that you ingest in, and you can do transformation on this field before it is ingest to extract certain field, for example. They asking like something similar to um to do this. So
yeah, you could definitely in fact that's recommended. You want to generate the embeddings first before you land them into a database, and in this case, Pinot. Here's the issue here. Uh, Embeddings, if you recall, have a fixed length. When you generate an embedding, in our case, I think it was about over 1,500 uh, length array, right? Length embedding. When you create embeddings, let's say from a really large video or an image or really like a web page with thousands and millions of text, that's going to be bigger than you would think. That was going to be bigger than that capacity of 1,500 size embeddings. What the model does, what the embedding model does, is actually compresses all that information into the fixed size embedding size. In this case, over about 1,500 sized embeddings. Right. So that actually makes it more efficient when you're sending data over Kafka, because Kafka has a limit on some data sizes. When you're storing it into Pinot, you have storage issues when you have like really big um, uh, um, data being landed there. So there's a capacity issue at the end when you're moving and storing data. So it's really important that I think to create the embedding as early as you can before you actually send it on the wire into Apache Pinot, and maybe not do what I'm doing, where I'm actually parsing all the content, putting it into a database. You want to maybe just reference, um, go, uh, go out and read page, and then send that to the LLM. I'm kind of cheating here by putting the content actually in the database, the database itself in Pinot. But I recommend actually going out and pulling that information from where they live, so that you're not incurring the storage and transfer costs of that data.
okay, I think we are. Let me quickly check last time. Um, I can say that our stream is quite successful, so we can have a bunch of the bots joined our stream, which is meaning that we, appeared on some of the real-time dashboards. Now, with this, I don't see any other questions. So, folks, if you have any questions about this, we do have a open source Pinot Slack channel where you can ask a question. Me and Hubert, we hang out there all the time together with some awesome folks from the Pinot community and the Pinot engineering team. Also, we do have a Startree Slack channel where you can ask questions about Startree. Um, if you're not sure how to start play around with the recipes that we shared. We have a quick start, and please try. If you don't want to maintain your own infrastructure, try our free forever trial. No credit card needed. You can start in a second and start exploring Pinot. And after that, you can decide if it's something that solves your problem or not. I would like to say thank you to Hubert. He was doing this a lot of research on this topic, and always fascinates me like how far this research is going. Thanks for your Dan for helping organizing this meetup. Stay tuned for more events in future. We're trying to do more and more live events here on the LinkedIn, YouTube, and Twitter. If you're watching us there, I see at least um, at least 64 people watched us on the Apache Pinot Twitter, and 70 people in Startree the Twitter, which is fantastic. Thank you for your support. And with this, it was Hubert. My name is Victor, and don't forget to have great day. Take care, folks. Bye.